Hey everyone, another day, another DSA problem. So today we're going to look at today's daily problem. That's 2095. Delete the middle node of a linked list. And that statement itself is very self-explanatory. Honestly, this is a very simple question. I don't know why they've mentioned it as medium. It should actually be an easy. So yeah, they just basically want us to go to the middle here. In this case, it's the node 7. They want us to delete that node. So 4 would just point to 1, and this would become 1, 3, 4, 1, 2, 6. In this case, this is the middle node. So that would be 1, 2, 4. And in this case, it's just 2. So yeah, in the case of that, there was only one node, we'd just be returning none. So I'll still just can explain this here. All right, so we want to find the middle node, which is the first thing. So we already know of a method. If you guys don't know, then I would suggest that you look into this. But yeah, so the slow and fast pointer method is something which will give us the middle node of the linked list. And one thing we want to do is we want to keep a track of the node before the middle node, because that's where we're going to change the assignment of next, right? So we want to keep track of a previous that points to the node that was before our slow pointer. All right, so then we just delete the middle. How do we do this? We're going to point that previous node to the node after the slow pointer, whichever node it's pointing to, and then we're just going to return head. So and I mentioned earlier, right? So in the case of, in this edge case scenario where there's only one node, I don't think we need to even do this. We'll just return none because we're deleting that node itself, and all we have left is nothing. So yeah, let's take this example over here, which is, I think, the same example that they've given. So for people who don't know what the slow and fast pointer method is, we'll check that here, right? So what we do is we initialize a slow pointer and we initialize a fast pointer, both pointing towards, like pointing at the head, like the starting element, right? And in this case, let's also have a previous, okay? So I'll just write it down here. So we have slow, fast, and previous, all of which are pointing to whatever the starting element was, right? And this is how the code is. So we check while fast and fast.next, we are going to update. So we want to keep track of the element, the node which was before the slow pointer, right? So I'm going to update that first before slow gets updated. So it's going to equal to slow. Slow will point to the element after itself. So this, and fast will move 2 times the speed of slow. So fast is equal to fast next. So this is just the standard code. By the end of this, you actually have slow pointing towards the middle element and previous pointing towards the element after this. Let's just do a dry run to kind of check this out. All right, so we're doing slow is slow.next. So slow is pointing here and previous is pointing here, right? And then fast is fast.next. So fast comes here, right? And then after that, previous would be pointing here, and then slow is equal to slow.next. So then slow comes here, fast goes to fast.next, right? So this is where my fast would be, okay? And now, again, previous will take this position, slow will go to the element after itself, which is this. So slow now points here, previous points to the node before slow, and fast is equal to fast.next. So fast ultimately goes to the end. And what do? We are checking if the next element exists, right? And fast.next is none. So I know that if this condition, if this satisfies and I can no longer do another iteration of it, then it means that my fast pointer has ultimately reached my end. My slow pointer has ultimately reached the middle node, and my previous, in this case, is pointing to the node before it. So here's what I'm going to do. So I know that this is my previous node, right? Maybe I should change the color. So 4 was the previous node, and I know that 7 is like the middle node, right? So I will just make 4 point to whatever slow is pointing to, and that will essentially just remove this here, and I get what I need, right? Okay, I hope you guys understood that explanation. It is a very simple problem. So this is basically just going to take time complexity of, just write that down. So it's going to take a time complexity of O of n, and the space is just O of 1 because we're not using any extra space. Okay, let me just code this up real soon. Yeah, one thing I wanted to check was if there's only one element, so I can do this by checking. If not, head dot next, meaning the next element itself was none, then I can just go ahead and return none immediately. Or else I want to initialize my slow, fast, and previous, all which will point to head. And I can write my condition fast, while fast, and fast dot next. Then I want previous, first of all, to be given the value of whatever the slow pointer was pointing to. And then I want slow to move. So next, and then fast is going to move twice the speed of slow. So, right? So by the end of this, previous is the node previous to the middle element. So I'll just do previous dot next is equal to slow dot next. And at the end of this, I should just be able to return whatever the head was. And yeah, as you can see, it works. Let me just write the complexity here. As we mentioned, time was O of n because we have to iterate. It's actually n by 2 because we go to the middle, but yeah, that's still, we're removing constants and that's O of n. So, and then space is just O of 1, right? So yeah, this is today's daily problem. It's very simple, and happy coding, everyone.